Einstein's equivalence principle led him to a radical vision. Gravity was not a force pulling objects through space, it was the shape of space itself. Matter tells space-time how to curve, and curved space-time tells matter how to move. To grasp this, he abandoned the Newtonian picture of invisible attraction. Instead, he imagined space-time as a vast, flexible fabric. Place a massive object like the sun on this fabric and it warps under the weight. A smaller object like Earth moves not because the sun pulls it, but because it follows the curved geometry around it, just as a marble rolls along a dented rubber sheet. This metaphor is imperfect but powerful. In reality, space-time is four-dimensional, and the curvature is not a literal bending into some higher space, but a change in how distances and durations are measured. Straight lines, the paths of least resistance in Newton's flat space, become geodesics, the natural trajectories within curved space-time. What looks like acceleration under gravity is simply an object moving straight along a curved surface. This insight demanded new mathematics. To describe curvature precisely, Einstein turned to the geometry of Gauss and Riemann, fields of mathematics that treated space as something that could be stretched and folded. Each point in space-time had its own geometry, defined by a set of equations describing how nearby points related to one another. Gravity, in this view, was not a mysterious influence, but the expression of those relations. When Einstein finally understood this, he realized he was not just reformulating physics, he was rewriting the architecture of reality. Newton's universe had been built on absolute scaffolding. Einstein's universe was dynamic, self-interacting, and alive. The geometry of gravity was no longer background. It was the stage, the actor, and the script all at once.